What is light? How does it differ from darkness? By the late 19th century, light was known to be a form of energy, transmitted or radiated, emitted from one group of atoms, and often absorbed by another. Scientists developed a useful model of this radiation, the electromagnetic wave. Light behaves as an electric wave, interacting with a magnetic wave, propagating through space at over 300,000 kilometers per second. This wave model explains most, but not all, behaviors of light and other forms of radiant energy. At the turn of the 20th century, a German physicist tackled one of these unexplainable behaviors. His name was Max Planck, and he was interested in the way energy was shared by atoms and the space between them. Electromagnetic theory could not predict the results, which were observed by using a closed box, in which radiation bounced back and forth. But Planck found a way to mathematically predict the actual observations of energy distribution. He proposed that atoms are restricted in the way they radiate energy, and that each atom can only emit discrete, measurable bundles of energy. Planck called such a bundle a quantum. He proposed that the energy of each quantum emitted is determined by the frequency of the radiation. In other words, it is equal to the frequency times a constant. Planck roughly calculated this constant, and he used it to predict energy emissions by atoms. This quantum idea revolutionized physics when another brilliant physicist, Albert Einstein, carried Planck's ideas a step further. He applied the quantum idea to what is known as the photoelectric effect. This effect can be studied by sealing two metal plates in a vacuum and connecting them to a battery, which induces an electric charge on each plate. If the negatively charged plate is coated with potassium, then illuminated with blue light, electrons are emitted from the negative plate and attracted to the positive plate. But if red light is used, no electron flow occurs. Before Einstein, scientists tried to explain and predict this relationship between light and electric current using the electromagnetic wave model. Their prediction? When electromagnetic waves strike atoms, energy is transmitted to the electrons. Some of the electrons escape from the atoms. Since red light did not cause emission of electrons, it should only be necessary to increase the intensity of the red light to transfer more energy to electrons and produce emission. That's the prediction. In fact, it fails to happen, no matter how bright the red light is made. But any radiation with a frequency equal to or greater than blue light does cause emission, even if the light is faint. What's more, the wave model also predicts that more intense light at these frequencies will transfer extra energy to the electrons. In fact, it does not. Increased intensity simply makes more electrons flow. These observations just can't be explained with a wave model. So Einstein used Planck's quantum idea instead. He proposed that atoms cannot simply absorb any amount of radiation. They can absorb only discrete bundles or quanta of radiation. This can cause atoms to emit electrons. But why the difference between blue and red light? Planck had already proposed that for emitted energy, the energy of a photon is proportional to the frequency. So a higher frequency means more energy. Einstein proposed that the same reasoning could be applied to absorbed energy. Red light shining on a potassium-coated electrode produces no emission because individual photons of red light do not have enough energy to liberate an electron from a potassium atom. But blue light photons do have enough energy to liberate potassium electrons. The quantum prediction. Even higher frequency photons have more than enough energy to produce emission. The excess energy transfers to the electrons. And that's just what happens. What's more, the quantum idea predicts that if the intensity of light is increased, it means greater numbers of energy bundles. More bundles means more atoms can absorb energy and release more electrons. So the quantum idea predicts an increase in electron flow. This prediction, too, matches what happens. So we have evidence that energy is emitted from Planck's atom in a quantum and absorbed by Einstein's atom in a quantum. It seems logical to assume that electromagnetic radiation is comprised of bundles. Einstein called these bundles photons. But the photon hands us a new problem. What exactly is a bundle of waves? Waves are continuous and are described by their wavelength. A bundle is a concept better described not by a wave, but by a particle. Thanks to Planck and Einstein, the particle model of light, long discredited, was rediscovered. The wave model was still essential to understanding. Light and other electromagnetic radiation seem to require not one or the other, but both models. With this discovery, the modern era of quantum physics was born.